Good afternoon, gentle folks, surfers, wave riders everywhere, beach dwellers everywhere, science and weather nerds everywhere. Um, have you ever met a surfer that wasn't a weather nerd or wasn't interested in ocean science? I have not. Um, find me one. That is my challenge for you today. In the meantime, we're going to talk science, and we're going to talk science to surfers, to coastal dwellers, and to everyone, to all the peoples. As a surfer and a science nerd, this is important stuffs, and that's the reason why we're going to do a special report today at the OBX Wave Report on the science. Yesterday, we dove into what the climate scientists are talking about. One of my favorite climate scientists is Stefan Ramsdorf, and he's also a surfer. So some intersection there. But right now we're gonna talk about some of the things that Zach Alabe, a climatologist and polar observer, one of the top polar observers in the world, highlighted to me yesterday, um, is that global sea ice is at record low levels. And as we mentioned yesterday, this is a major climate indicator. This is like a canary in the coal mine. And I'm starting right here at this graphic provided by Zach Labe. It's a reanalysis of National Snow and Ice Data Center information and put together in a graphical representation that is very striking. And so, for example, right now we've got global sea ice here in the range of, on the left side of the graph, we've got extent, and that's in millions of square kilometers. And right now, global sea ice in the range of about 16, looks like about 16.1 million square kilometers. This is 2023. And then we have this list of subsequent record low global sea ice years. Where various years showed record sea ice during certain times of the year. And for 2023, we've had record low sea ice on the global measure for a good portion of January and then into late January and early February. And you can see the progression. It's not just that this record low is an outlier in a normal state. You can see where the record lows have fallen in the past. So up here, you've got earlier years where the record lows were in the range of like 19 million or 19.5 million square kilometers at this time of year, maybe closer to 20. And at the top of the monitor in the earlier time frames, like in the 1980s and 1990s. And then as we head down to the present, you see that the new record lows are considerably lower than they were in the past. And this is indicative of a warming Earth system driven by climate change, which is driven by fossil fuel burning, and the warming ocean in particular, because the sea ice sits on the water, the ocean surface, and as the oceans heat up, the ice shrinks. It's very simple, very direct, very dramatic. The impacts of the loss of sea ice, though, are not simple, and they can cascade. They are multitudinous, potentially. Sea ice is highlighted as a potential tipping point for the climate system. And sea ice is a protector of the Earth. It helps to stabilize our climate. It reflects some of the sun rays back into space, creating like a reflectivity that is called albedo on the surface of the ocean. But if you trade white reflective sea ice with dark absorptive ocean, you get more absorption into the waters, which can have a compounding snowball effect on certain climate regions in the world. And we have the polar regions of the world warm faster with the more fossil fuel you burn. And part of the reason for that is the way that greenhouse gases trap heat in the Earth system, but and spreads it out, tends to spread it out more evenly across the world. But another aspect is that you have this process that I encourage you to research and listen to the experts about called polar amplification. And polar amplification is how warming is more dramatic at the poles due to certain processes that occur as things warm that can result in more heat being captured in the Arctic. And one of them is the loss of sea ice, that trading of the reflective ice with the darker surface of the ocean. Um, and we're seeing that now. We're seeing that as we have burned a lot of fossil fuels. We've trapped a lot of heat into the atmosphere. That atmospheric heat has been absorbed by the oceans. The ice has melted. The oceans have gotten darker. They've absorbed more heat near the poles. And this is starting to create a worrying dynamic with regards to our glaciers as warmer waters get ever closer to the glaciers. Um, we are in a state of climate emergency and crisis, but this is not an irreversible state if you listen to the scientists. But there is the warning that is happening now, and the warning is for urgency, not for panic, because we do not need to panic. We do not need to react in a harmful way. We just need to stay focused on the stable path forward that we have. And that stable path is in the transition away, the rapid transition away from the burning of the fossil fuels that is trapping all this heat in the Earth system, and toward clean energy, which is going to replace the fossil fuels with energy systems that do not emit carbon into the atmosphere and cause this progression of loss of sea ice, the polar amplification of the heat, the threat to our glaciers, the threat of more rapid melt, and the threat to our coastlines. We can do this. We can manage this rationally without doing the crazy. We can. Um, I have faith in our better angels. And if we listen to facts and reason and morality, we can do it. All right, so let's talk about this. Let's talk about this in a rational way, in a not freaking out way, but also let's talk about it in a way that produces the right sense of gravity and gravitas and seriousness as it relates to our situation. Okay, so this is a NASA Worldview satellite shot of Antarctica on February 1st, right now. And the story of record low global sea ice is a story of Antarctica and the Arctic. It is a story of heating oceans. It is a story of heating airs over those oceans. And it is a story of feedbacks, of the handshake between the loss of that reflectivity and the darker waters that absorb that extra little bit of heat. I say little, that extra bit of heat over time that has kind of a compounding impact. And right now, over Antarctica, there's considerably less ice than there normally is. In the northern regions of Antarctica, and I'm going to shift to, there's an Antarctic map that I have here to give you guys like a little geographical reference. In the Weddell Sea right now, sea ice is about normal. But as you head over to this region, which is the Bellinghausen Sea and the Amundsen Sea and the Ross Sea, sea ice is dramatically reduced. And then as you head over toward East Antarctica, sections near Dumont d'Urville on Antarctica and the Bali Islands are also considerably lower than normal. And the net result is that, and you can see this in the satellite shot, there's practically no sea ice in the satellite shot in this region here, in the Ross and Edmundson Sea region. And there's practically no sea ice on this side of East Antarctica. And the net result is that sea ice for Antarctica is at record lows. And Antarctica right now, and this is summertime for Antarctica, is driving the new global record low. And I'm going to switch to a sea ice monitor provided by the National Snow and Ice Data Center. And so you can see this. You see this line, the orange line, that is the median ice edge from 1981 to 2020. So that's where basically the ice would tend to have been in 1981 to, I'm sorry, 1981 to 2010. So that's where the ice would tend to extend to. And as you can see, there's these large areas of open water in the Amundsen and like Ross Sea area. The um, Weddell Sea is about normal here. Some areas where it's a little bit less, some areas where it's a little bit more. And then around the East Antarctic edge, you've got some areas there about normal, but then other areas where sea ice is dramatically reduced. And so the Antarctic sea ice is in record low ranges, and that is helping to drive the global sea ice into record low ranges. And then looking at the Arctic, I'm going to go ahead and zoom in here at the ice concentration monitor. You can also see that there are areas of the Arctic, pretty much all over the Arctic, where sea ice is reduced from the median ice edge of 1981 to 2010. You see these large areas of open water here. And looking at the graphs in the monitors, we find that the Arctic sea ice is near record low levels. And this is the University of Bremen model, which is also helping to drive the global record low. It's the Arctic, it doesn't seem to be as impacted, but maybe I'm wrong. But the Antarctic is pretty dramatic in its loss, actually. Like looking back and forth now, it seems like the extent losses are about equal between the Antarctic and the Arctic. So certainly record low sea ice in the Antarctic and record low to near record low sea ice in the Arctic. What is driving this? I mean, the main thing that is driving the loss of sea ice is this accumulation of heat in the ocean system. And the climate scientists have been talking about this and talking about this and talking about this for weeks and weeks and weeks and months and months and months. And the ocean heat accumulation, the top 2,000 meters of the Earth ocean system is at record highs. And the ocean is the main heat sink for the global system. We got more heat in the oceans than we do in the atmospheres. There's more energy potential in water. Specific heat is a big deal for the oceans. And that heat in the water is obviously helping to drive that sea ice melt. There's weather conditions at the surface that help to do that as well. Winds help to affect sea ice extent. High pressure systems and low pressure systems, the relative location of the two, also help to change it. But this is the main um, beast in the um, the main Godzilla in the system here. This is the main driver of it all. And so you got various weather trends on top of that. But the big thing, the thing that we do not want to ignore is the heat in the ocean system. And that heat is at record high levels. And this is driven by fossil fuel burning. All right, now looking at the ocean surface. Now the ocean surface is one indicator. The global heat in the ocean system in the top 2,000 meters is another indicator. But this is just at the ocean surface. And what I'm looking at here is at anomalies. This is in the region of what is normal and what is above normal based on climatology. And so for Antarctica, and the area in Antarctica that we're most focused on is this area that's from, say, 68 degrees south latitude on further toward the pole. So in this zone here, in the 68 degrees south latitude-ish range, and then southward. And in that region, you can see that there's a lot of above normal ocean surface conditions here in the Edmundson Sea and in the Ross Sea area, and that's helping to drive that melt. You've got near normal temperatures here, maybe slightly cooler than normal temperatures, but not by much here in the Weddell Sea area. And then over toward East Antarctica, you've got near normal to slightly above normal conditions in some locations. One of the regions where you've got less sea ice, you've got slightly above normal conditions at the ocean surface. So it looks like above normal conditions that are basically temperature conditions, both at the ocean surface and in the air, that are helping to drive that sea ice melt, but likely also some deeper waters, some higher, just generally specific heat in the ocean system, helping to melt that ice in Antarctica. Now, overall, for the global ocean system, temperatures are much warmer than normal at the surface. There are exceptions. There are parts of the Southern Ocean here where temperatures are cooler than normal, but the overall ocean surface conditions are warmer than normal. For the equatorial Pacific, we have a state of La Nina that is slowly shifting back to a El Nino neutral state. And what's ironic here about La Nina is La Nina tends to be a period of global coolness at the surface. And though we have cool pools over parts of the globe, the net is that the global ocean system is still warmer than normal despite La Nina, which would tend to make a cooler than normal ocean as the variability in the Earth system dips toward the cool state. So we're in the cool state at the surface, but the average is much warmer than normal. And we have record low sea ice, which is an indicator of that. Now, globally, of course, we also need to look at the Arctic for sea ice. And you can see now very dramatically in the Arctic that ocean water temperatures are much warmer than normal in the near Arctic, much more dramatic than the Antarctic, at least in this monitor. And of course, you still have some cool pool regions, but for the most part, overall, ocean surface temperatures in the Arctic much warmer than normal. And that's helping to drive that loss of sea ice that we see. All right, now looking at the atmospheric monitors, I want to show you the predicted temperatures for the next, I believe this is a 10-day. Yeah, I think this is a 10-day model. And what I want to show you is the warmer to much warmer than normal conditions that tend to invade the Arctic region in particular, and then parts of the Antarctic as well. And I'm just going to let the model run. And then this is also another anomaly map. So the areas in blue are cooler than normal. The areas in red are hotter than normal. And overall for the globe, we've got hotter than normal conditions. Overall for the Arctic, we've got, I say hotter than normal, but just above normal conditions for the Arctic, and ranging from above normal to rather above normal to much above normal. And then for the Antarctic, we have near normal conditions in the atmosphere to slightly above normal temperature conditions. And I'm just going to show you guys these indicators here at the bottom of the model. This is a climate reanalyzer. This is taking global data from the NCEP climate forecast system and the CFS reanalysis of the CFSR model frameworks, and then just making a reanalysis of it through the graphic that you see here. And what you see here is like that the Arctic is much warmer than normal. It's the region of the world that is showing the most change from human-caused climate change right now. And you see temperatures ranging from 1 to 2 degrees Celsius above normal throughout the entire 10-day period. For Antarctica, the temperature shifts from, looks like about negative 1.2 degrees Celsius in the anomaly to positive I believe, oh, negative 1.8 to, I think it's like positive 1.8 degrees Celsius, 1.9. Okay. So yeah, so ranging from negative 1.8 to positive 1.9 in the model, but overall a little bit warmer than normal across the Antarctic as well. This is in the air. Also with the oceans warmer than normal as well. So, I mean, that's the story of it primarily, that the air temperatures and the ocean temperatures are warmer than normal to much warmer than normal. We've got building heat in the ocean system, and possibly that the weather has become more favorable generally for lesser ice extents in the Antarctic and the Arctic as well. And so we have new record global lows driven primarily by human caused climate change. This level of record low would not be the case in a normal climate system. All right. And so that is our deeper dive into what's going on with the sea ice. We do have a record low sea ice right now. And as I have mentioned before, I'm going to go back to the NASA worldview to show you the white glacier covered continent of Antarctica. And the march of the sea ice closer and closer to these glaciers precedes a march of warmer waters to the glaciers that sit on the coastline, and many of them sit in the water. And so when the sea ice recedes, you get more warm waters near the coast, moving both at the surface and under the glaciers. And that extra heat has an effect on the glaciers. It speeds up their melt. And it tips the balance in Antarctica to loss of ice. And that tipping of the balance does threaten the coastlines here in the Outer Banks and across the world. And so sea ice makes a difference. Sea ice is a buffer, it's a defender of our glaciers, and we want to keep that. And so we want to do our best to transition to clean energy as rapidly as we can. Dr. Michael Mann has indicated that we need to reduce our global carbon emission by 50% over the next decade to prevent the rising of global temperatures above 1.5 degrees Celsius above baselines, and thereby prevent catastrophic climate change. So the emergency is here now in the climate. We're seeing the beginnings of the emergency, but we have the time right now to do the things to help protect the glaciers and the sea ice and the oceans and the coastlines. And that thing is to mass deploy clean energy. So please do everything you can to help save our beautiful coastlines by helping to speed the clean energy transition to wind and solar and electric vehicles primarily, um, and to other renewable energy sources as well. So thank you for joining me for this special edition of the OBX Wave Report, where we did a deep dive into the icy regions of our world, which protect our coastlines if they remain stable, and which can hurt our coastlines if they are driven to melt. So thank you for joining me again, and I will be back